Father, Father, I'd like to talk to you for a minute.
Oh, why does everybody in the family wait until I'm reading the financial news to interrupt?
Well, I'm sorry, Father, but this is important.
Oh, all right. Well, how much do you need this time?
Oh, it's not money, Father. It's about Peter.
Yeah, that young whippersnapper. Well, what about him?
He's coming over tonight to talk to you.
Oh, that should be very dull indeed.
Father, don't be like that. He's going to... he's going to ask... Well, we want to get married.
What? Married? Have you lost your mind, Hazel?
Oh, please, Father. Listen, Peter's very bright. He's going places, and he's just wonderful besides.
Yes, and being bright and wonderful won't pay the bills.
But Peter just got a job. He can support me.
How much does he make?
Well, $20. But he'll get raises. He can't help but succeed.
$20, huh?
Mm-hmm.
Do you realize that I give you that much a week for an allowance? Huh. What does this embryonic tycoon do?
He's a he does important work in a bank. Oh, Father, don't sneer. All great men have started at the bottom. Look at Abraham Lincoln. Look at you. You started by selling newspapers.
And carrying along that theme of humble beginnings, look at the X-ray. The X-ray has risen from comparative obscurity to a place of prominence as a valuable tool in science, medicine, and industry. The apparatus used in X-ray work has become more and more intricate as time has passed. On this excursion in science, we're going to have an opportunity to become acquainted with a mighty new tool of science and with the generation of 100 million volt X-rays. Our science reporter gleaned the facts from Dr. E.E.Charlton of the General Electric Research Laboratory, a co-designer of this huge machine, the betatron. And here is Emerson Markham with the details.
Thank you, Bob Stone, and how do you do, everyone?
Before you go on, Emerson, just exactly what is a betatron?
Well, Bob, the name betatron has been given to a device which can be perhaps more completely described as an induction electron accelerator.
I'm wondering, are the betatron and the cyclotron one and the same thing?
No, the cyclotron is a device which accelerates positive charged particles in discontinuous steps by the repeated application of an electrostatic field, a DC magnetic field being used only to cause the particles to spiral around in the vacuum chamber. The betatron accelerates negative charged particles at a continuous rate by an electromagnetic field generated by an AC magnetic field. This AC magnetic field also serves to keep the particles traveling in a circle in the chamber. Now, both devices are capable of developing high-energy particles. In the cyclotron, the high-energy positive charged particles, such as protons, deuterons, or alpha particles, may be used to bombard light elements with the production of neutrons. In the betatron, the high-energy negative-charged electrons may be used to bombard heavy elements with the production of X-rays.
Emerson, is the fundamental mechanism of producing X-rays with a betatron the same as discovered by Röntgen back in 1895?
Yes, it's always the same as discovered by Röntgen, namely by accelerating electrons to a high velocity and suddenly stopping them by collision with a solid body, the so-called target, interposed in their path.
Well, how does the betatron differ from other X-ray generators?
With the usual type of X-ray generator, the electrons are accelerated to high velocity by an electrostatic field applied between the cathode and the anode of the X-ray tube. Now, in the betatron, the electrons are accelerated to high velocity by a time-varying electromagnetic field. You can compare the induction electron accelerator, or betatron, to an ordinary transformer.
How do you do that, Emerson?
Well, it has a laminated iron core and a primary coil. But in place of the usual secondary coil with many turns of wire, there is placed a highly evacuated donut-shaped glass tube with a hot cathode electron gun which emits an electron beam similar to the cathode of a conventional type of X-ray tube. The electrons are shot at a tangent into the tube and are caused by the time-varying magnetic field to circle around within the vacuum tube, acquiring with each revolution the same voltage increase as though they had flowed through a single turn of wire. The electrons are magnetically guided while they are being continuously accelerated in the circular path in the vacuum tube, and at a chosen time, they are magnetically guided away from the circular path and made to strike a target and produce X-rays, or emerge from the vacuum enclosure as high-energy electrons.
What does this betatron look like?
Well, the iron core or magnet is constructed by joining 100,000 pieces of sheet silicon steel together. This magnet is 15 feet long, 7 feet wide, and 9 feet high. It weighs 130 tons. The magnetizing coils which energize the magnet have over 2 tons of copper in them and carry 1,000 amperes of current at 24,000 volts. A 24,000 kVA capacitor bank made up of 1,000 units is used to provide a high power factor for the input to these coils. The glass vacuum tube is shaped like a donut with an outside diameter of 74 inches. The hole in the donut is 58 inches across. In cross-section, the tube measures 8 inches horizontally and 5 inches vertically.
What kind of power is the machine operated by, Emerson?
Oh, 60 cycle power, Bob. The electrons are injected into the vacuum donut in short pulses when the magnetic field is zero, and their speed increases constantly as long as the field is increasing in strength. During the time the field is increasing from zero to its maximum value, the electrons, magnetically guided, run around the vacuum enclosure 250,000 times, picking up with each encirclement of the field an average energy corresponding to 400 volts, thus acquiring a total energy corresponding to 100 million electron volts. As the donut is about 6 feet in diameter, this means that the electrons travel nearly 800 miles during the quarter cycle. And as the magnet is energized by 60 cycle current, the electrons travel that distance of 800 miles in 1/240th of a second. When the electrons have reached their maximum energy, by suitably changing the distribution of the magnetic field, they are directed away to collide with the target and produce 100 million volt X-rays.
What can these X-rays be used for?
Well, in industry, the betatron will increase still further the range of thickness of metal structures that can be effectively radiographed and inspected. In medical therapy, the increasing depth dose of ionization produced in body tissues with these more penetrating X-rays may be found to be more useful, particularly in the treatment of deep-seated lesions. In scientific research, the machine is useful in fundamental studies with higher energy X-rays in the field of nuclear physics. Studies of the effects on the internal structure of the nucleus produced by bombarding matter with these high-energy X-rays may give us new and important fundamental knowledge.
Well, these powerful rays are so penetrating. Isn't there danger to the people working around this machine?
Oh, they do have to take considerable precautions to safeguard everyone from the radiations that are emitted. A special building with very heavy concrete walls, over 3 feet thick, was constructed to house it. The machine is operated from a control room shielded from the X-ray generator by protective barriers of steel and concrete. People aren't allowed in the X-ray generating room when X-rays are being produced. The X-ray target in the vacuum donut is so placed that most of the 100 million volt X-rays, which are produced in a fairly small defined cone of 2 degrees, are emitted in a direction away from all personnel. A cloud of very energetic electrons is also emitted from the machine. Direction and distance are factors that must be utilized to the utmost as protective safeguards when experimenting with such penetrating radiations of high intensity.
Could a machine for accelerating electrons be built to produce still higher voltage X-rays?
Yes, electron accelerators can undoubtedly be built to produce still higher voltage X-rays. Just what the voltage limits are is as yet unknown. When the electrons are running around in a circular orbit, they will radiate some of their energy, and this must set a limit somewhere to the energy that they can be made to acquire. The radiation problem plays a small role at 100 million volts, but it might make it somewhat more difficult to reach 1 billion volts.
Emerson, how do these X-rays compare with the cosmic rays of old Mother Nature?
Well, Bob, the 100 million volt X-rays are entering the cosmic ray part of the radiation spectrum. But Dr. Charlton says that scientists must be very humble about it. After all, he says, when Röntgen discovered X-rays, he was generating them with a little over 10 to the 4th power volts energy, about 25,000 volts. The 100 million volt machine produces X-rays with 10 to the 8th power volts energy, or 100 million volts. Scientists have observed cosmic rays produced by nature with energies as high as 10 to the 16th power volts, or 10 million billion volts.
That is a lot of volts.
Well, don't be alarmed, Bob, about these cosmic radiations coming from stellar space. You can't stop being constantly bombarded by them anyway. But fortunately, the intensity of their radiation that hits your body is extremely feeble in comparison with that which you could receive if you were to stand in the X-ray beam in front of the 100 million volt X-ray machine for just a few moments. The advantage of generating these high voltage X-rays in the man-made machine is that you can stop the intense radiation whenever you choose by simply opening a switch. Dr. Charlton said that progress has been made in the last 50 years in man-made machines generating X-rays at higher and higher voltage levels. But nature would still need a very powerful microscope to observe our puny efforts in comparison to her own in the generation of ultra-high voltage radiation.
Dr. Charlton certainly practices what he preaches, about scientists being humble, I mean. Our thanks to him and to you, Emerson, for a most interesting story. And ladies and gentlemen, if you would like to have a copy of a paper by Dr. E.E.Charlton of the General Electric Research Laboratory, a paper which contains the story we've just brought you and more facts besides, for instance, more of a description of the possible applications of 100 million volt X-rays, all you have to do to get a copy is address your request to Excursions in Science in care of the station to which you are now listening, asking for scientific paper number 230, entitled A Mighty Tool of Science. That's scientific paper number 230, A Mighty Tool of Science. Your copy will be put in the mail for you free of charge. And now, once again, it's time to start considering the scientific questions which you listeners have sent in to us for answering. The answers you will hear are as reliable and up to the minute as they can be, since they reflect the thinking of staff members of the General Electric Research Laboratory or of other equally trustworthy institutions. Well, Emerson, if you're ready, let's begin our question-answering stint by considering first this letter which reaches us from a lady who would like to know how to clean a copper bathtub.
Well, now, there are three possible remedies for that particular dilemma, Bob. One is the use of dilute hydrochloric acid. Another is the ordinary household ammonia and water mixture. And the third and final is the use of salt and vinegar, that is, wetting the salt with the vinegar. It would be best to rub the copper well with any of these mixtures and wash off all the acids after treatment.
Our next customer says, I have been told that a well won't run dry if enough water is drawn from it. In other words, if there is a 30-foot deep well and the water level is, say, 20 feet, if the water is kept below the level, it will increase the water that flows into the well. Is this correct?
Water will run from the outside into the well faster the more water you draw from the well. If the outside reservoir stays full, the well will never run dry. Now, this is the general rule, but there are sometimes exceptions, of course.
Next in the order of business is this one. It comes from a lady who wants to know, to what extent are the inert gases soluble? Also, she asks, are they easily liquefied?
All inert gases are somewhat soluble, but not as soluble as more chemically active substances such as carbon dioxide and ammonia. They are liquefiable at various temperatures. Helium requires the lowest temperature to become liquid. In general, though, you wouldn't say that they were easily liquefiable.
Next, a listener asks if parsnips that were planted in the spring can be eaten in the fall, or if it's better to wait until the next spring. And our friend would also like to know if they should be covered with leaves in winter.
Parsnips may be eaten at any time or stage of ripeness. They get better as they get riper and are better after spending the winter in the ground or in a good storage because more of the starch is changed to sugar and they are sweeter. They should be covered enough to prevent freezing, which does them some harm, although not much.
Now we come to this letter from a young man who would like to know the answer to this question. If you wanted to cool some very hot water in a cool room, would you use a metal or a wooden pail, and why?
Well, if you wanted to cool some very hot water in a cool room, you should put it in a receptacle that would quickly transmit the heat of the water from it. Since metal is a much better conductor of heat than wood, a metal pail would be better.
Next, how about this one? How often do moon eclipses occur, and at what time do they usually occur, day or evening?
Eclipses of the moon always occur at full moon, but they don't occur at every full moon. When the moon is full, it is opposite to the sun and therefore visible only at night. Consequently, an eclipse of the moon can be visible only at night time. Of course, when it is night in one half of the earth, it is daytime in the opposite hemisphere.
Now a listener in Erie, Pennsylvania asks what the space between the nucleus and the revolving electrons consists of.
Between the nucleus and the revolving electrons in an atom, there is empty space.
And we'd better start making the space around here just as empty, and the sooner the better. For once again, our time is up. So I'd better say thank you, Emerson Markham, and goodbye, everyone, until our next excursion in science.